Good evening everyone. So this is tutorial 2. In this tutorial we're gonna learn how to implement a project on an FPGA using CloudV. Our project would be controlling the rate of the change of the RGB LED on one of the lattice boards, which is the iCE40 UltraPlus Breakout Board. First let's go ahead and open CloudV, sign in, create a new repository, we'll call it tutorial 2, and description RGB project. Let's make it private. Let's open the workspace. Okay, so the project is controlling the rate of the change of the RGB LED. In order to do that, we need a clock source. We will be using the clock source on the FPGA, but the clock source on the FPGA has a frequency of 12 megahertz per second. So in order for our eyes to observe the change, we need to divide this clock. So we need a clock dividers. So basically the main role of the clock divider is having an input clock, and it outputs a clock with the desired frequency. So let's create a new module. We'll call it clock divider. So our module is going to take 2 inputs and it will have only 1 output. So input clock, input reset, output let's call it clock out. Okay, now we need 2 parameters. The first parameter is the input frequency and the second parameter is the output frequency, so that when we declare an instance of our module, which is a clock divider, we will just provide the input frequency and the output frequency that we want. So let's create the first parameter. Let's call it n and give it a value of 1. So this is our output frequency. Our input frequency, let's call it c and give it a value of 12 for simplicity. Okay, now we need a counter to count how many cycles have passed for this input clock, so that the output clock should toggle. In this example, when the input clock when the counter reaches 6, that means the output clock should toggle or change from 0 to 1 or from 1 to 0. So let's declare a counter, 32-bit counter. We'll call it counter. Now we need two always blocks. The first always block will control the clock out, and the second one will control the counter. So let's create the first always block. So always at positive edge of the clock, begin, end. And if we encounter a reset, our clock out will equal to 1. That means it's gonna start with 1. Else, in this case, if the counter is 6, that means the clock out should toggle. So if the counter equal c over n times 2, we toggle the clock. Else, the clock should stay the same. So clock out equal previous clock out. Okay, now we need to create another always block for the counter. So let's copy and paste this. Always at positive edge of the clock. If we encounter a reset, our counter is going to be 0. Else, if the counter equal to c over n times 2, the counter goes back to 0. Else, we increment the counter. Okay, now let's validate our module, but before validating it, let's set it as top module. Click validate. Okay, the module passed verification successfully. Let's create a sample test bench to test our module. So new Verlo test bench. Next, create. let's create our clock source. So always #5 clock equal to not clock, and we do a reset here. Wait for 20, reset equal to 0. Okay, let's go ahead and simulate. Okay, so let's zoom in. We can observe that when the input clock made 12 cycles, our output clock made only 1 cycle. So from a 12 hertz frequency clock, we have an output clock of 1 hertz. Now we need to create a project to drive the RGB LEDs of the board. So let's create a new module. Let's call it test RGB. Our module is going to take 2 inputs, the clock, let's call it clock input, and the reset, and we wanna control the RGB LEDs using the toggle switches on the board. So we have 4 toggle switches on the board. We're gonna use one for the reset, and the other 3 we're gonna use to control the rate of the change of the colors of the RGB. So let's create another 3 inputs, which are switch 1, switch 2, and switch 3. And we will have 3 outputs, which are RGB0, RGB1, RGB2, and they control which color should be displayed on the RGB LED. So output reg RGB0, RGB1, RGB2. Okay, now we need to declare 4 instances of our clock divider, so that we have 4 versions or 4 frequencies to control our rate of change of the RGB LED. So, but before doing that, we need to declare some wires to hold the outputs of these 4 instances. So let's declare wire called clock 1, clock 2, clock 3, and clock 4. And let's declare a wire called clock, which would be our main clock that we're going to use to control the LEDs. Okay, so let's create the first instance, so clock divider. The first one, we're gonna pass for the output frequency 1 hertz, and the input frequency is the frequency of our clock source on the board, which has 12 megahertz. So 12 megahertz. And let's call this instance div1. We're going to send clock input, and our reset, and the first one is going to output on clock 1. Let's copy this and paste it. We're going to create 4 instances. Let's say the second one will have an output frequency of 5 hertz, third one 10, the second one 10, and the third one is 15. Let's change the name of the instances, div2, div3, and div4, and this is going to output from clock 2, clock 3, and clock 4. Now we need to assign our main clock to any of these versions depending on these 3 inputs, which are the toggle switches. So let's do that. Assign clock equal So if S1 is 1 and the rest are zeros, our clock is going to be equal to clock 2, else if S1 is 0 and if S2 is 1, S3 is 0, it's going to take clock 3, else S1 is 0, S2 is 0, and S3 is 1, it's going to take clock 4, else it's going to take clock 1. Now we need an always block to control our three outputs, which are the RGB0, RGB1, and RGB2. But first we need a counter to control which color should be displayed, or which value of these RGBs should be used. So let's declare a new counter. We'll call a 32-bit counter. We'll call it counter. And let's create an always block to control our counter. So if we encounter a reset, we're going to display the white color. The white color is all of these values are zeros. So RGB0 equal 1, RGB1 equals 0, and RGB2 equals 0. So RGB0 equal to 0, RGB1 equal to 0, and RGB2 equal to 0. And the counter goes to 0. Else, if we don't increment, if we don't receive a reset, or we don't encounter a reset, we increment our counter. So counter equal to counter plus 1. And now we check for the value of the counter, and depending on which value of the counter, we display a different color. So if the counter equal 0, we display white. Else, can take this one. Else, if the counter is 1, we display a different color. Since we have 3 bits, let's create all the different combinations to get all the different colors. So let's take this, copy and paste it a couple of times. So if the counter is 0, RGBs are 0, 0, 0. If the counter is 1, 0, 0, 1. If the counter is 2, 0, 1, 0. If the counter is 3, 0, 1, 1. If the counter is 4, 1, 0, 0. If the counter is 5, 101. If the counter is 6, one one zero. If the counter is 7, 111, and we make the counter equal 0. So it returns back to here. Okay, now let's validate our project. So let's first set it as top module. Okay, now our project is ready to be implemented on the FPGA. So in order to program the FPGA and upload our design on it, we need two things. First, the pin constraint file and the bit stream file. To generate the pin constraint file, we go to File, New, pin constraint file. And here you choose the board that you're using. We're using the iCE40 UltraPlus Breakout. Create. So here is the inputs and outputs of our model, and we need to map these inputs and outputs to the to that of the FPGA. I created here a file. So here is the pin out information for the UltraPlus Breakout Board. But I created a file for the tutorial for our inputs and outputs. So our clock input is going to be on 35, the switches 23, 25, and 34. Our reset on 43. Our RGBs on 39, 40, and 41. So let's do that. The clock on 35. The reset is on 43. S1 23. S2 25. S3 on 34. Our RGBs, RGB 0 on 39, RGB 1 40, RGB 2 41. And then you click save. Now we have our constraints file here. The next step would be to generate the bit stream file. To do that, you go to project and generate bit stream, and here you choose the constraints file. You could have multiple constraints files for the same project, but now we have one, so we'll just click generate. Okay, so our bitstream file is created here. It's going to be named as a top module.pin, which is test RGB. You're going to find it on the build folder right here. So now we have our project ready to be uploaded on our FPGA. But before uploading it, we need to know how to upload it. I'm using a tool called iCE40. In order to use that, you go to iStore project, and scroll down, and you need to install these prerequisites to be able to use the tools. And you only need the tools, you don't need these other things. So you just install these tools, and if you're using Linux, you need to run this command to change the permission for the USB driver to upload the bitstream file on the FPGA. Okay, so now let's go ahead and download our project. So you go back to CloudV and download the .pen file. Okay, before uploading it, there are some settings that that you need to make on the board. So there are two options to program the FPGA. There is the Proc Flash option and there is the Proc iCE option. The Proc Flash option, save the project or the program on the FPGA, while the Proc iCE programs the FPGA using direct SRAM. So we're gonna use the I recommend using the Proc iCE, because if you use the Proc Flash and if your program is faulty, you might cause damage to the FPGA. So the Proc iCE option, for the Proc iCE option, you need to configure the jumpers in the vertical position. So you need to change the jumpers on J6 to the vertical position, and you program with the iceprog/s your bitstream file name .pen. So let's do that. So first, change the jumpers to the vertical positions and go to the place where you downloaded your bit file. Let's open the terminal. Let's go to downloads. Okay. So for Proc iCE, you write iceprog -s test rgb.pen. If you're not using the Proc iCE and you're using the Proc Flash, you just remove the -s and hit enter. Okay, so now the FPGA is programmed. You should now see the colors of the RGB LED changing every second. So let's see that.